Welcome, friends. I'm so glad you're here. Whether you're drifting toward sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the very beginning of Earth, into the time when it is no more than molten stone, glowing in the dark of space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The dew. Earth begins as heat. A small sphere gathers in the quiet violence of the solar system, where countless fragments of rock and metal circle the newborn sun. Gravity draws them inward, and every impact sends shock waves through the forming planet. The surface is an ocean of magma, restless, glowing orange-red, releasing a haze of vapor into the still black sky. This is no place for life, not yet. Only the raw churn of matter in transition. Minerals separate in the chaos, heavy iron sinking. Toward the center, lighter silicates rising toward the surface. A layered planet slowly takes shape. The core becomes dense and metallic, the mantle a shifting sea of molten rock, the crust fragile and thin, like a skin that cannot hold. Even in this state, the beginnings of Earth's magnetic field stir, a shield that will one day protect oceans and air. The irony, of course, is that this protective field is born in a world with nothing yet to protect. Tiny zircon crystals, some no larger than grains of sand, form in these early conditions. Billions of years later, a few will survive as the oldest. Known pieces of Earth, recording temperatures, chemistry, and the presence of water long before oceans exist in their full form. It is remarkable that such small fragments carry the memory of an entire planet's childhood. Another irony, that the most delicate crystals endure while mountains vanish without trace. The heat seems endless, but in time, radioactive decay, collisions, and core formation stabilize and cooling begins. It takes not years or centuries, but millions upon millions of years for the planet to calm. Only took an eon to set the stage, and still it is only the first step. Yet mysteries remain. No one can say with certainty how quickly the surface hardened or how long magma oceans endured. The record is erased again and again by later upheavals. Scientists read what clues they can, but much of this earliest chapter is silence. A silence that endures across 4.5 billion years. The irony is quiet and simple. The most violent beginnings create the stillness we live within now. Without impact, no Earth. Without heat, no crust. Without chaos, no stability. The planet rests beneath the weight of space, but peace is fleeting. From the outer solar system, fragments of rock and ice continue to arrive. They strike with unimaginable force, releasing more energy than whole mountain ranges will ever hold. This era is remembered as the Late Heavy Bombardment, a time when Earth, Moon, and the other inner planets bear scars of a rainstorm measured not in drops but in craters. On the Moon, those scars remain sharp and unweathered. On Earth, the surface is too restless to keep them. Continents shift, oceans boil away and return, and the evidence of that storm is swallowed into the mantle. With each impact, molten rock splashes outward and new gases rise to the atmosphere. Some collisions bring volatile elements, carbon, nitrogen, and water, delivered in flecks of cometary ice and asteroid minerals. It is strange to consider that the oceans we know may have arrived in fragments, scattered from elsewhere, and yet this scattered origin becomes a single body of water surrounding the planet. Only took billions of deliveries, but eventually the ices will stand. Irony lingers in the record. The most destructive strikes may also seed the conditions for life. Worlds sterilized again and again, yet within those resets lies nourishment. Another irony whispers from the moon. Without those same impacts, the surface of our satellite would be smooth, and the tides that later guide life might never rise and fall with such regular rhythm. And a third irony. Earth's own craters vanish beneath tectonic churn, leaving silence where chaos once reigned. Still, mysteries remain. The precise intensity and duration of this bombardment are debated. Did the rain of debris last 100 million years, or only a fraction of that time? Did it peak in violence or taper gently? The truth is locked inside shattered asteroids and ancient lunar basins, beyond the reach of perfect certainty. The planet endures. Rock melts, oceans flash to vapor, skies darken with dust, yet Earth persists. To imagine the world in this state is to imagine restlessness embodied. No quiet. Seas, no green coasts, only the echo of collisions under a dim young sun. Amid the chaos of collisions, one event surpasses all others. A body the size of Mars, moving with silent inevitability, meets the young Earth. The impact is so complete that both worlds merge and scatter at once. Metal sinks into Earth's core, while a spray of vaporized rock arcs outward into orbit. Over time, this luminous debris gathers into a sphere, the Moon. The Moon cools and hardens quickly compared to Earth. Its surface, frozen in place, preserves a record of this creation, a record Earth itself cannot keep. The irony here is gentle. Our planet loses its own earliest scars, but the Moon carries them in plain sight, as if remembering on our behalf. Another irony follows. Earth gains stability from this accident. The tilt of its axis steadies, seasons become more predictable, and tides rise and fall with the pull of the new companion. And a third irony. From one catastrophic collision comes the quiet glow that has guided countless lives through night. Dust settles across Earth's surface after the impact, yet the planet is never quite the same. Rotation slows as the Moon drifts away, centimeter by centimeter each year, an imperceptible retreat shaping the length of our days. The gentle analogy often offered is that of a dance. Two partners circling, each shaping the other's movement, though one partner slowly steps back. A scientific mystery endures. The exact conditions of this impact remain debated. Did Theia strike directly or glance at an angle? Was the Moon formed from Earth's own mantle, or from the mingled remains of both bodies? Each model tells a slightly different story, and the evidence is written in the isotopes of lunar rocks. Yet even those samples carried back by human hands leave space for uncertainty. So Earth spins, steadier than before. Oceans have not yet fully gathered, continents have not yet risen, but above the molten crust a pale companion now circles, patient, enduring, and silent. The sky begins to cool. Steam condenses, vapor falls, and for the first time, rain gathers on a surface that can hold it. At first, the water sizzles on still warm rock, vanishing into mist before it can pool. But over time, the balance shifts. Droplets survive, streams form, and basins collect them. What had been a planet of fire begins to hold oceans. Water comes from more than one source. Some arrives from comets and hydrated minerals carried on colliding asteroids. Some is released from Earth's own mantle, vented as gas, and cooled into liquid. Two origins joined into one sea. The irony lies in the duality. The oceans feel seamless, yet their molecules carry stories of two very different journeys. A second irony is the sheer abundance, an entire surface wrapped in blue, born from countless grains of ice no larger than dust. And a third irony. The seas that will someday cradle life are at first only a solvent for stone, dissolving minerals into their depths without witness. These first oceans are heavy with dissolved iron, giving them a greenish cast under the dim young sun. No waves roll against sandy beaches. There is only rock, tide, and water. Stillness spreads outward, broken only by volcanic islands that rise and sink again. Scientists trace these beginnings through zircon crystals, which hint at liquid water as far back as 4.3 billion years ago. Yet mysteries remain. How quickly? Did the oceans gather? Were they stable, or did early impacts boil them away again and again before calm finally arrived? The record is fragmentary, like pages torn from the start of a book. Overhead, the moon pulls on these waters, lifting them and letting them fall in long tides across the barren coasts. With each cycle, the connection between planet and satellite deepens, written in motion rather than words. Like a planetary exhale, Earth breathes out steam, and what remains is an ocean. The oceans settle into their basins, hushing the glare of stone, and the skin of the world begins to thicken. Basalt wells up from the mantle and spreads beneath the water, dark and dense, cooling from black glass to fine-grained rock. It fractures into hexagonal columns and swells into rounded pillows where lava meets seawater, each pillow a frozen sigh of heat into cold. Quiet ridges trace the sea floor, not yet the well-ordered lines of later ages, but restless seams where new crust forms, faster than it can rest. The planet exhales melt, and the surface learns to hold it. Basaltic crust dominates at first, rich in iron and magnesium, heavier than what will come later. It forms quickly and sinks easily, a conveyor of heat from the deep interior to the surface, a pathway for gases to meet the sky. Mantle temperatures run higher than any later epoch, and some eruptions pour forth ultramafic komatiites, hot enough to flow like thin oil, smooth and swift. Where a flow breaks into water, it wrinkles into bulbous pillows that stack in gentle heaps, a submarine garden of stone. Tiny vesicles capture the last breath of bubbles, and minerals line those empty spaces like small, crystalline skins, a delicate varnish on a world still learning the word delicate. Amid this dark substrate, something lighter begins to appear. When basalt is hydrated and carried downward, or when it melts under pressure in thickened portions of crust, a new melt rises, poorer in magnesium, richer in silica and sodium. It solidifies as tonalite, trondhjemite, and granodiorite, the TTG suite, pale compared to basalt, buoyant compared to mantle rocks. These bodies of felsic rock gather into domes and blocks, stitched with quartz veins and flecked with feldspar, that glints even in dim light. Buoyancy becomes architecture. The lighter stones ride higher, and the beginnings of continents, small, irregular, and scattered, stand a little above the sea. On some far future shield, a fragment of this story endures, gneisses with faint banding, zircon grains with cores older than the host rock, slivers of crust that date to over 4 billion years. Their oxygen isotopes whisper of interactions with liquid water before the oceans fully claim their breadth. The image is steady, light crystals nested inside darker rock, like frost set in ash. These ancient pieces lie today in places like the Canadian Shield and the outcrops of Western Australia. But in this early time, they are merely rising rafts, drifting in slow silence on a warmer mantle stream. The geologic process is simple in outline and intricate in detail. Heat moves outward. Rocks melt where pressure, water, and composition align. Less dense melts rise and crystallize. The cumulative effect is differentiation, a sorting by weight that turns a uniform beginning into layered complexity. Isostasy, the balancing of masses on a deep, deformable interior, raises felsic blocks as if they float and pulls dense basalts down as if they were anchors. The crust achieves texture. Greenstone belts sag like keels between pale TTG domes, serpentinized, Mantle fragments carry the memory of water deep into the lithosphere. Late dikes cut clean through older fabrics, adding dates like notches on a quiet clock. Beneath, convection cells stir the mantle with long, slow spirals. Heat flow is several times greater than in later ages, and the lithosphere is thinner, weaker, easier to ruck and fold. Some regions thicken enough to founder and drip back into the mantle. Others are heated at their roots by mantle plumes that well up like slow flames. The interplay of plume warmth and surface cooling sculpts a patchwork of volcanic plateaus and felsic uplifts, a jigsaw of microcontinents separated by spreading sea floor. The world acquires edges and sutures, not yet the sweeping arcs of later mountain belts, but seams nonetheless. A lesser-known detail lingers in the pillows and banded rocks that accumulate in shallow basins. Chert layers, pale and glassy, precipitate from silica-rich waters and sandwich between basalts and volcanic lastic. Sediments. Within those cherts, tiny stromatolitic laminae sometimes begin to accrue, the first murmurs of biological structure gathering on the margins. Elsewhere, spheral layers, round grains formed from impact-ejected melts, settle like a fine hail into the sedimentary record. Even when the focus is stone, the waters carry whispers of both skyfire and early life's patience. The exact timing of Earth's first continental rise stays uncertain. Some models argue for an early start to subduction-like recycling, with hydrated basalts sliding beneath buoyant blocks. Others suggest a stagnant lid regime evolving gradually toward mobile plates, with crust dripping and delaminating rather than cleanly subducting. The rocks preserve pieces, not a continuous film, and the planet's earliest tectonic choreography remains a quiet debate written in zircons, isotopes, and metamorphic signatures. How quickly did granitic masses accumulate? How continuous was the buoyant lid? The questions sit like clear pools where the record breaks. The first irony is gentle and persistent. The continents, which stand proud and dry, owe their existence to water. Without hydration to lower melting temperatures, without fluids to mobilize silica, the pale rocks would not rise, and land would remain a basaltic floor beneath a global sea. The second irony rests on the scales. The lightest rocks carry the greatest weight in human history, supporting soils, forests, and cities, while the truly heavy world, the iron core, the dense mantle, stays unseen, unwalked, and unknown except by inference. And the third irony is temporal. The oldest surviving crystals are older than the oldest surviving rocks, so memory survives as grains carried by younger stones, like elder voices housed in younger bodies. In this slow ascent, the planet practices balance. Rafts of TTG rise, cool, and fracture. Greenstone belts thread between them with volcanic and sedimentary layers. Metamorphism imprints foliation where pressure and heat tighten the weave. Each cycle of heating and cooling writes another page. In the crust's structure, gneiss domes swelling and relaxing, shear zones slipping in tiny increments, dikes freezing from melt and becoming the next generation's walls. The surface now is not smooth but patterned, a quiet mosaic of buoyancy and strength. Komatiites, with their spinifex textures, long bladed olivine crystals that grew quickly from superheated lavas, cool into fans and herringbones that point back to a hotter mantle. Pillow basalts preserve ripple-like forms where lava met seawater no warmer than memory. TTGs weather into sandy feldspar grains that later will fill riverbeds, though rivers are sparse and short for now. Each texture is a timestamp, each mineral a thermometer, each isotopic ratio a diary entry written in a hand that never hurries. A modern analogy drifts from the kitchen to the cosmos. As a pot of thick soup cools, a skin forms on top. Steam condenses beneath. Light droplets ride to the surface while heavier ingredients sink and simmer. Earth is not soup, and yet the direction rhymes. Light to the top, heavy to the bottom, circulation carrying heat outward in a slow, steady unfurling. The difference, vast yet familiar, is only time. What takes minutes in a pot takes hundreds of millions of years beneath the sea. Only took a fraction of a billion years for land to lift itself a few hundred meters above the tide. Over the wide basins, the moon lays its hand upon the water and draws the sea back and forth across raw shorelines, washing chemical traces into fractures that will later metamorphose into veins of quartz and carbonate. Rain, thin and acidic in a CO2-rich air, leaches elements from newborn rocks and returns them to the ocean, adding to the slow ledger of weathering and deposition. The carbon-silicate balance begins to hum faintly in the background, a thermostat, too sluggish to notice day by day, yet determined across epochs. The planet grows quieter in its heat, not because it is cool, but because its patterns now repeat. Basalt spreads, TTG domes rise, greenstone keels settle, and the cycle continues. The buoyant parts of the crust stitch themselves together into larger rafts. Sutures heal even as new ones form. There is no drama in this, only a deepening of form. The Earth, having learned to build a crust, now learns to keep it. Above the new crust, gases gather into a restless cloak. Volcanic vents release carbon dioxide, water vapor, nitrogen, and sulfur compounds into the air. The early atmosphere is thick with haze, unbreathable, heavy with heat. Lightning arcs through its density, illuminating clouds streaked with ash. Beneath it, oceans lie green with iron and restless with volcanic input, sealed under a roof of shifting vapor. Carbon dioxide dominates, joined by methane from hydrothermal systems, a mix that traps heat despite the faintness of the young sun. The irony is quiet. The star glows weaker than it does today, yet the Earth is kept from freezing by its own exhaust. Another irony lies in the nitrogen that fills the sky in abundance. The very gas that later becomes the background of life's breath is at this time an inert presence, silent and unused. A third irony is the sulfurous haze, choking to any modern creature, yet a veil that softens ultraviolet radiation, offering a shield long before ozone arrives. Volcanic outgassing is constant. Every eruption adds to the balance of air and sea. Some gases dissolve into the water, acidifying the young oceans and leaching minerals from basalt. Some rise into the sky and condense, returning as rain. This circulation binds air, water, and rock in a single system that stabilizes over immense spans of time. The surface becomes a laboratory of chemistry, though there are no observers, only the quiet persistence of reactions. A lesser-known detail lingers in ancient rocks. Inclusions of gas trapped in tiny mineral cavities preserve the fingerprints of this atmosphere. Ratios of nitrogen to argon, traces of noble gases, and isotopic patterns are read today as evidence of the sky that once was. In some cases, the trapped gases are billions of years old, a memory sealed in crystal, held through pressure, heat, and change. Still, mysteries endure. How thick was this atmosphere? Was it warm enough to counter the faint sun entirely, or did intermittent glaciations still occur? Did methane-producing microbes arrive early enough to matter, or was volcanic release the dominant driver? The numbers shift with each model, and the sky of deep time resists a single image. Yet in its haze and density, the early atmosphere carries a quiet continuity. It links fire with water, crust with cloud, mantle with sea. Every exhale of the earth becomes part of its breath, and every drop of rain is both return and renewal. Amid the haze of the young atmosphere, the rocks themselves keep quiet records. Within ancient outcrops, fragments of zircon appear. Small, durable crystals of zirconium silicate. They measure no more than the width of a grain of sand, yet they are the oldest surviving solids of Earth's crust. Some are dated to more than 4.3 billion years ago, making them relics older than any mountain, older than any ocean basin still in place today. Zircons form when molten rock cools and crystallizes, incorporating uranium atoms into their lattice. Over time, uranium decays to lead, and the ratio becomes a clock, measuring ages across billions of years. These clocks survive even when the rocks that host them are broken, metamorphosed, or melted again. The irony is striking. Great land masses rise and vanish, oceans open and close, yet the story is carried not by continents but by crystals no larger than dust. Another irony lies in their beauty. A gem mineral used in jewelry today is also the hard record of Earth's most inaccessible past. And a third irony, though zircons are nearly indestructible, the rocks they prove existed. Ancient felsic, crust and weathered surfaces are gone, erased by the very tectonics that zircons help us imagine. Some zircons contain inclusions of minerals like quartz, indicating that they formed in the presence of liquid water. Their oxygen isotope ratios suggest interaction with the hydrosphere at very early times, hinting that surface waters cooled and cycled sooner than once believed. A few even preserve tiny bubbles of fluid, microscopic capsules of an ancient world sealed inside. But mysteries remain. Did these zircons crystallize in stable continental crust, or only in fleeting protocontinents that never endured? Was early Earth a world already holding oceans and weathering, or one where such moments were rare and unstable? The crystals speak clearly about their own age and composition, but less clearly about the landscapes in which they grew. They endure nonetheless, carried in younger sandstones, found in riverbeds of later ages, polished by erosion yet unbroken. They are fragments of time out of place. Like fossils of minerals rather than organisms, they hold the memory of conditions long vanished. And in their stillness, they remind us that even at the smallest scale, Earth preserves the trace of beginnings. The Earth begins to regulate itself. With continents rising in scattered rafts, with oceans blanketing the low ground, a long and steady cycle begins between air, rock, and water. Carbon dioxide released by volcanoes dissolves into rain, forming weak carbonic acid. That rain falls across new crust, weathers feldspar and basalt, and carries dissolved ions, calcium, magnesium, bicarbonate, down into the sea. There, the carbon is trapped in sediments and buried into stone. Over time, this becomes the carbon silicate cycle, a planetary thermostat that whispers across billions of years. The irony is soft but persistent. The slowest cycle imaginable controls the most fragile thing of all, climate. Only took millions of years for a feedback system to arise that counters the faint young sun. Another irony rests in the rocks themselves. The destruction of mountains by weathering is what keeps the oceans liquid. And a third irony. The gases that choke the sky eventually help to set the stage for breathable air, not by remaining, but by being drawn down into stone. Silicate weathering is patient work. Raindrops strike basalt, leach cations, and flow outward, in rivers that no creature yet drinks from. The chemistry is relentless, a quiet transaction between water and mineral. Each atom of carbon removed from the air lowers greenhouse warming just slightly, cooling the planet, while volcanic exhalations replace it. A balance emerges not by design but by repetition, each side of the cycle answering the other. Evidence of this exchange is subtle. Ancient carbonates in greenstone belts hold isotopic signatures of atmospheric carbon, their ratios whispering of climate fluctuations even in the Archean. Some models suggest this balance kept Earth from freezing, entirely despite the sun shining at only 70% of its present power. Still, the details are uncertain. How quickly did the cycle respond in a hotter world with thinner crust? Did land area limit its strength, or did hydrothermal alteration of seafloor basalt play the larger role? These questions remain suspended, unanswered but enduring. The image is quiet. Rain falling across volcanic islands, dissolving minerals into thin streams, carrying them to the shore. In time, each drop becomes part of limestone on the seafloor, part of a cycle so vast that it gives Earth its equilibrium. Like a long, slow breath, the planet inhales carbon from volcanoes and exhales it into stone. Across the surface of the restless Earth, fragments of land rise and drift. These are not continents as known today, broad and steady, but smaller blocks, microcontinents and cratonic seeds, buoyant rafts of felsic crust afloat on denser basaltic seas. They gather from repeated melting, stitching together quartz, and feldspar-rich masses that resist sinking into the mantle. Each fragment is a survivor of a process that destroys nearly everything it creates. The irony is gentle. The oldest parts of Earth are also the most fragile, preserved not because they are unchanging, but because they happen to float. Another irony lies in their scale. These small pieces, no larger than islands, will one day anchor entire continents. A third irony lingers in their endurance. Although they drift endlessly, they appear in the present as if they had always been stable, yet their origins are chaotic and fleeting. These early blocks rise higher than the basaltic crust around them, forming shallow shelves where water pools and evaporates. In tidal zones, thin microbial films may already begin to trace the edges, though the evidence is faint and often erased. Above, volcanic arcs add new material, while below, greenstone belts sag between granite domes, marking sites where crust, thickened and deformed. Each block is a balance of buoyancy and pressure, a raft pushed and pulled by currents of mantle heat. Geologists find their traces today in the oldest cratons. The Acasta gneiss complex of Canada, the Itsak gneiss complex of Greenland, the Jack Hills of Western Australia. These regions preserve zircons older than 4 billion years, tonalite, trondhjemite, granodiorite domes, and metamorphic belts that tell of early tectonic stress. Yet mysteries remain. Did true subduction already occur? Or did crust founder in drips and delaminations rather than clean slabs? Were these fragments long-lived or constantly recycled, with only rare survivors left to tell the tale? Still, the image is clear enough to linger on. Scattered islands of stability in a sea of fire and iron. Their shapes drift slowly apart and together, endlessly rearranged, yet they are the first hints of the continents to come. At the boundaries of heat and water, chemistry grows restless. Deep beneath the oceans, where tectonic fractures open pathways into the mantle, seawater seeps down, heats, and rises again. It emerges through vents as black smokers and white smokers, plumes rich with hydrogen, methane, and metals. Around these hydrothermal chimneys, minerals precipitate into towers and mounds, creating sheltered pores and labyrinths of stone. Within those tiny spaces, gradients of temperature and chemistry unfold, and here perhaps the first shadows of life begin. One accepted view holds that these mineral structures offered a natural reactor. Iron-sulfur surfaces catalyzed reactions. Proton gradients powered energy transfer, and simple organic molecules assembled into more complex chains. The irony is subtle. Life may have begun in darkness, nourished not by the sun, but by the heat of Earth's interior. Another irony follows. The first cells may have relied on the very conditions that today seem most hostile: boiling water, crushing pressure, toxic chemicals, and a third irony. While the surface world was unstable, bombarded, and volatile, the depths of the sea offered the calmest refuge. The detail is striking. Modern hydrothermal vents host towering edifices of sulfide minerals, colonized by lush ecosystems of microbes, worms, and clams. In the Archean, there were no animals, no plants, only chemistry threading itself through stone. Tiny pores in precipitated minerals may have served as natural membranes, confining molecules into compartments where chance reactions became self-sustaining. The mystery endures. Was life's spark lit here, or in shallow pools under the sky, or in some other environment entirely? Experiments reproduce pieces of the puzzle, forming amino acids, nucleotides, and simple lipids, yet no experiment recovers the full path from chemistry to biology. The record is gone, erased by time, leaving only indirect hints in the shared machinery of cells. Still, the vision is quiet and persistent. Beneath a dark ocean, mineral towers rise in silence. Plumes drift upward into the water, and within their hollow chambers, molecules explore the first outlines of life. Within the watery labyrinth of early Earth, strands of matter learn to copy themselves. Among the possibilities, one molecule draws particular attention: ribonucleic acid, or RNA. It is capable of holding information in its sequence of bases, and in certain forms, it can also catalyze reactions. In this dual role, both message and tool, it seems to many scientists a likely intermediary in the rise of life. Short strands form from nucleotides, perhaps assembled on clay surfaces or within mineral pores at vents. Some sequences fold upon themselves, creating pockets and loops that speed up reactions. A chain that helps itself replicate has an advantage, though the process is fragile and error-prone. The irony is quiet. From imperfection, progress arises. Another irony follows, that molecules so unstable in modern laboratory conditions may have persisted in the harsh early oceans. And a third irony lingers. A molecule, once only a chemical curiosity, becomes the universal thread of life, even though today DNA has taken its role as the main archive. Small details make the image vivid. Laboratory studies show that certain clays, such as montmorillonite, can encourage nucleotides to link into longer chains. Minerals may have served not just as scaffolds but as participants in the chemistry. Tiny lipid vesicles, spontaneously formed in water, can encapsulate RNA strands, creating a primitive version of a cell. Within these delicate spheres, molecules find shelter, concentrating the reactions that would otherwise diffuse into nothingness. The mystery remains unresolved. Was RNA truly the first replicator, or were there earlier, simpler systems? Peptides, mineral surfaces, or other chemistries now lost? Did the transition to DNA and proteins come gradually or in sudden leaps? The answers are obscured by billions of years of change, hidden by the success of life's later forms. Yet the vision is steady. In pools, in vents, in microscopic compartments, molecules of RNA fold and copy, sometimes failing, sometimes persisting. With each repetition, chance bends toward order, and Earth carries the first quiet steps toward biology. The oceans of early Earth deepen into strange colors. Without free oxygen in the air, the seas hold vast amounts of dissolved ferrous iron, lending them a green or even rusty hue depending on local chemistry. Sunlight filters weakly through the haze above, and beneath the surface the water is dim, heavy, and metallic. Life, if present, survives not by breathing oxygen, but by drawing energy from chemical gradients. The irony is clear. The oceans that appear lifeless to us are in fact rich in the very elements that will later become essential for metabolism. Another irony follows. The iron that today rusts tools and stains stones was once invisible, dissolved and unseen, until oxygen revealed it. And a third irony. Though the seas seem abundant with potential, they remain silent for millions of years before any visible change occurs. In these iron-rich waters, hydrothermal vents continue to feed dissolved metals into circulation. Volcanic islands add still more through erosion and rainfall. The chemistry is restless but contained, a vast buffer waiting for a trigger. Modern analogs exist in small, oxygen-poor basins, where green layers of ferrous iron drift beneath the surface, faint echoes of a world once global in scale. Yet mysteries endure. How stable were these iron oceans? Did local oxygen oases form early, only to vanish again? Did ultraviolet light at the surface drive partial oxidation, creating bands of ferric iron that later settled as sediments? The evidence survives in ancient rocks, but the pathways remain contested, their details blurred by metamorphism and time. Still, the image is steady. Imagine seas with no blue, no clarity, no fish or plants, only a dim metallic glow under a weak sun. In that silent chemistry, the stage is set for the next transformation, the slow release of oxygen that will turn green oceans to red stone. Above, the metallic seas, the sun shines with only 70% of the brightness it has today. This faint young sun should leave Earth frozen, its oceans locked in ice. Yet liquid water endures, stretching wide across the planet, a contradiction that puzzles scientists still. The warmth comes from greenhouse gases, carbon dioxide, methane, perhaps ammonia, released in abundance by volcanoes and sustained by the slow feedback of weathering. The first irony is soft but striking. A weaker star sustains a warm world, while a stronger future sun will one day threaten to overheat it. A second irony lingers in the gases themselves. What is poison to future animals is salvation to the earliest oceans. And the third irony, the planet's thermostat is so slow that it allows glaciers to advance and retreat on scales of millions of years, yet across the sweep of time, the seas never fully vanish. Geochemical records provide traces of this puzzle. Isotopes in ancient carbonates suggest climates warm enough for liquid water. Yet, glacial deposits dating back billions of years hint at intervals of freezing, episodes when the balance faltered. The faint young sun paradox endures. How did Earth maintain such delicate equilibrium with so dim a star? Was methane more abundant than expected, perhaps sustained by early microbial life? Or did the carbon silicate cycle operate more effectively than models predict? Small details sharpen the vision. In some Archean-banded iron formations, layers show rhythmic variations that may reflect seasonal cycles or shifts in climate. In others, microtextures hint at biological mediation. The rocks carry not only chemistry but time, quiet pages in the diary of a planet balancing warmth against weakness. Still, the image rests in silence. A sun, too faint to sustain warmth, a world that should be frozen, yet oceans ripple against, volcanic shores. The contradiction itself becomes a form of stability, fragile, unresolved, and enduring. Within the iron-heavy seas, a new process stirs. Tiny organisms, cyanobacteria, begin to capture sunlight, using water as an electron donor and releasing oxygen as a byproduct. This is photosynthesis in its modern form, a quiet transformation that alters everything. The reaction is simple in outline. Carbon dioxide and water yield sugars and oxygen, powered by sunlight. Yet its consequences unfold over billions of years, reshaping oceans, atmosphere, and geology alike. The irony is immediate. The oxygen that sustains later life is at first a toxin, lethal to the anaerobic organisms that had thrived for eons. Another irony lies in its invisibility. For millions of years, oxygen produced by photosynthesis never accumulates in the air, vanishing into reactions with iron and sulfur instead. And a third irony, the most powerful planetary change comes from organisms too small to be seen, leaving only chemical shadows as their record. Details linger in stone, the presence of stromatolites, layered mounds built by microbial mats, marks shallow waters where cyanobacteria flourished. These structures, found in Archean rocks of Australia and South Africa, are among the earliest macroscopic traces of life's activity. Their laminae build slowly, one layer at a time, each trapping sediment and binding it with mucus-like films. Though modest in form, they become enduring monuments to photosynthesis. Mystery surrounds the timing. When exactly did oxygenic photosynthesis begin? Some evidence suggests traces of oxygen in rocks older than 3.0 billion years. Yet widespread accumulation does not appear until hundreds of millions of years later. Was oxygenic photosynthesis rare at first, confined to sheltered niches, or was it widespread but suppressed by chemical sinks in ocean and crust? The debate remains open, a reminder that life's most transformative step does not leave a simple signature. And still the image is steady. Under a dim sun, microbial mats, spread across tidal flats, releasing invisible plumes of oxygen into green seas. Each bubble is fleeting, but together they begin the slow reworking of an entire planet. As oxygen begins to trickle into the oceans, it meets the vast reservoir of dissolved iron. The reaction is immediate. Ferrous iron oxidizes to ferric iron, which is insoluble in water. Rust-colored particles form and drift downward, settling onto the seafloor. Layer after layer accumulates, alternating with darker bands of silica-rich chert, creating what will become banded iron formations. These striped stones, red and gray, are the quiet pages of Earth's earliest oxygen record. The first irony is stark. Oxygen's earliest work is not in the air, but hidden at the bottom of seas, locked away as stone. A second irony rests in abundance. The very process that clears the oceans of iron also prevents oxygen from accumulating for millions of years. And a third irony whispers from the rocks themselves. The stripes that appear decorative to us are simply the outcome of chemistry repeating itself, rhythmically, patiently, without design. Details make the vision tangible. Some banded iron layers are hundreds of meters thick, stretching across continents and deposits that will one day supply most of humanity's steel. Their lamination is fine, sometimes millimeters thin, reflecting cycles that may mark seasons, volcanic pulses, or variations in microbial activity. Magnetite and hematite dominate the red layers. Jasper and chalcedony shine in the pale. Even after billions of years, the patterns remain vivid, a geological memory written in rust and glass. Mysteries endure. Why do banded iron formations occur in distinct episodes rather than continuously? Did microbial blooms drive pulses of oxygen, release, or did volcanic gases and tectonic shifts regulate the chemistry? Were some layers biological in origin, others purely abiotic? The debate continues, with each interpretation leaving room for uncertainty. And so the image lingers. In quiet oceans, invisible oxygen rains down as iron-rich snow, settling into stripes of stone. What begins as waste from microbes becomes the framework for future mountains, a record as vast as it is silent. Over millions of years, the sinks that swallow oxygen, iron in the oceans, sulfur in volcanic gases, reduced minerals on land, begin to fill. Slowly, the balance shifts. Oxygen that once vanished as quickly as it was made starts to linger. Around 2.4 billion years ago, this change becomes irreversible, the Great Oxygenation Event. Free oxygen, for the first time, accumulates in the atmosphere. The ironies are quiet but sharp. Oxygen, a waste product of microbes, becomes the atmosphere's most defining component. Anaerobic life, which had flourished for billions of years, now faces toxicity from the very gas that will later sustain animals. And while oxygen is invisible, its consequences are not. Iron formations dwindle, red soils appear, and methane, once a greenhouse blanket, is oxidized away, plunging Earth into global glaciations. Geological signs carry the evidence. Red beds, terrestrial sandstones tinted by hematite, appear in the record after 2.2 billion years, signaling oxygen's reach into the air and soils. Sulfur isotopes show a shift as atmospheric chemistry changes from an anoxic to an oxic regime. Even tiny inclusions in detrital grains such as uraninite and pyrite vanish from river deposits because oxygen now weathers them before they can be transported. The entire surface chemistry of Earth is rewritten. Mysteries remain. Why did oxygen rise so suddenly after holding steady for so long? Was it a threshold in microbial productivity, a saturation of geological sinks, or a tectonic rearrangement that tipped the balance? Did continents growing larger increase weathering rates, amplifying nutrient delivery and microbial photosynthesis? No single explanation satisfies all observations, and the event remains one of Earth's most profound enigmas. Still, the image endures. The sky slowly clears of haze, the chemistry of oceans changes, and for the first time, oxygen becomes a permanent part of air. In silence, Earth inhales a new atmosphere, and nothing will ever be the same. As oxygen gathers in air and sea, the world tilts into paradox. For the countless microbes that evolved in an anoxic Earth, oxygen is poison. Their enzymes, tuned to chemistry without free O2, falter when exposed to it. Populations retreat into sediments, into deep oceans, into anaerobic refuges where chemistry remains as it was. At the same time, new organisms seize the opportunity. Aerobic metabolisms release far more energy from the same molecules, opening paths to complexity not possible before. The first irony is stark. What is waste for one group becomes power for another. The second irony is temporal. Life adapts to oxygen, but only after it has already transformed the planet. The third irony rests in the pace. It takes billions of years to accumulate oxygen, but only seconds for it to damage an anaerobe's cell machinery. The geological record carries this transition in muted colors. In shallow seas, oxidized sediments grow more common. In soils, iron minerals change hue. Red beds expand across continents, their ferric pigments preserving the presence of an atmosphere no longer reducing. Yet, deep waters remain oxygen-poor for hundreds of millions of years, a stratified ocean where anoxic chemistry persists below. The surface sky is new, but the deep sea remembers the old world. Mystery lingers in the details. Did oxygen rise smoothly, or in steps and pulses? Some evidence points to transient whiffs of oxygen long before the Great Oxygenation event, perhaps local blooms that flickered out. Others suggest secondary crashes in oxygen levels afterward, as sinks briefly reasserted themselves. The record is incomplete, leaving open whether the transition was abrupt or staggered, global or patchwork. The image is still. Microbial mats continue to release oxygen, layer upon layer, day upon day, without awareness of the revolution they sustain. For some, this new air is a silent catastrophe. For others, a hidden doorway. Earth itself does not choose. It only holds the balance of what survives. With methane stripped from the air and carbon dioxide drawn down by weathering, greenhouse warmth weakens. Ice begins to spread from the poles, creeping across continents and eventually reaching the equator. The planet becomes encased in glaciers. From shore to shore, oceans sealed beneath kilometers of frozen surface. This is snowball Earth, a silence of ice that endures for millions of years. The first irony rests in cause and effect. Oxygen, the gas that will later support warm-blooded life, helps trigger a global freeze. A second irony lies in the seas themselves. Liquid water remains beneath the ice, kept from freezing solid by geothermal heat and tides, yet inaccessible to the sky. A third irony follows in time. The harshest glaciations prepare the way for evolutionary expansions once the ice retreats. Evidence is written in stone. Glacial deposits appear on continents that once lay near the equator, their dropstones and striated pavements preserved in ancient sequences. Cap carbonates, thick sudden layers of limestone, overlie these glacial beds, marking the rapid return of warmth after the freeze. Isotopic ratios shift dramatically, signaling disruptions in the global carbon cycle during these extreme climates. Yet mysteries remain. Did Earth truly freeze over entirely, or did open waters persist near the equator? Were these events triggered solely by the loss of methane, or were tectonic positions and solar changes also involved? Did life nearly vanish beneath the ice, or did microbial communities survive easily in refuges below? Each possibility reshapes the image, but none can be fully proved. Still, the vision endures. A planet glittering in white, continents buried in glaciers, seas hidden under ice sheets that stretch to every horizon. Time passes in frozen silence, and Earth waits, suspended between starlight and stone. The stillness of global ice does not last forever. Beneath the frozen surface, volcanoes continue their work. Mantle plumes rise, rifts open, and eruptions exhale carbon dioxide into the air. With oceans sealed beneath ice, weathering of rocks slows, and carbon dioxide is not drawn down. Over millions of years, greenhouse gases accumulate, slowly, invisibly, until the balance tips. The ironies are layered. The very gas that once cooled the planet through weathering now warms it by absence of that same process. Another irony is scale. It takes only a few centimeters of volcanic ash to bury a local landscape, but it takes millions of years of volcanic breath to thaw a planet. And a third irony whispers in the rhythm. Ice sheets that seem eternal are undone not by sudden catastrophe, but by slow persistence of invisible gas. Evidence is captured in the cap carbonates that rest atop glacial deposits. These limestones form quickly, often with unusual crystal textures, as carbon-rich oceans re-equilibrate with a thawing atmosphere. Their sudden appearance marks the end of deep freeze, a geological exhale recorded in stone. Within them, carbon isotopes swing abruptly, reflecting the dramatic changes in global cycles. Mysteries remain. How high did carbon dioxide levels climb before the ice relented? Dozens of times modern values, or even more. How sudden was the thawing once the threshold was reached? Did the transition occur in decades, centuries, or millennia? And how did microbial life endure through the shifts, sheltered in brine channels within ice or in deep hydrothermal systems? The record offers clues, but not certainty. The image is steady. Ice cracks, oceans stir, and the sky grows heavy with greenhouse warmth. Glaciers retreat, rivers return, and continents reveal themselves once more. From silence of ice to floods of meltwater, the Earth re-enters motion, its pause ended by the persistence of fire beneath. As the ice retreats and warmth returns, the planet hosts a quieter revolution. Among the microbial lineages that persist, some cells take a new form. They enclose their DNA within a nucleus, surround it with membranes, and compartmentalize their chemistry. These are the eukaryotes, complex cells that will one day give rise to plants, animals, and fungi. Their arrival is not sudden in the record, but their significance unfolds slowly across deep time. The ironies are calm but profound. Complexity begins not in abundance but in scarcity. Eukaryotes are rare at first, confined to niches, their traces faint. Another irony lies in their origin. They arise from partnership, not independence, built from the merging of once separate organisms. A third irony lingers in survival. For all their complexity, eukaryotes endure side by side with simpler prokaryotes that had already thrived for billions of years and still do today. Small details sharpen the vision. Fossilized sterains, molecular remnants of eukaryotic membranes, appear in rocks over 1 billion years old. Microfossils with distinctive shapes, spiny vesicles, ornamented cysts, hint at their presence in Proterozoic seas. In laboratory, studies eukaryotic cells show the intricate machinery of endomembrane systems, cytoskeletons, and mitosis, all innovations absent in earlier life. Yet mysteries remain. Exactly when did the first eukaryotes arise? Was it before or after the harsh snowball Earth episodes? What ecological pressures favored their complexity? Predation, competition, or mere accident of symbiosis? And why did they remain limited for so long before diversifying? Each question highlights how fragmentary the evidence is and how much remains hidden in vanished oceans. The image is simple. In waters that once lay frozen, new cells float, each harboring compartments and membranes, each carrying the potential for future forms. They drift unnoticed in their own age, yet they are the quiet architects of all complex life to come. Within these new eukaryotic cells, an extraordinary intimacy takes hold. Once, free-living bacteria drifted through oceans, metabolizing energy on their own. Now, some of them are engulfed but not digested, retained instead as permanent residents. One lineage becomes mitochondria, supplying efficient energy through respiration. Another later becomes chloroplasts, capturing sunlight for photosynthesis. Symbiosis becomes identity. Separate organisms merge into one. The first irony rests in survival. What begins as engulfment, a prelude to death, becomes the foundation of partnership. A second irony lies in permanence. Endosymbionts that once lived freely lose independence, yet gain immortality by joining a host lineage. And a third irony whispers in continuity. Every breath of oxygen and every beam of sunlight processed by plants and animals today still passes through the descendants of those ancient bacteria. The details are quiet and intricate. Mitochondria and chloroplasts retain their own circular DNA, reminiscent of their bacterial ancestry. They divide by fission, not by the mitotic processes of their host. Their double membranes record the moment of engulfment, inner and outer, layers marking boundary and embrace. Ribosomes within them resemble those of bacteria more than those of eukaryotic cytoplasm. These signatures endure, embedded fossils of an event that shaped biology at its root. Mysteries remain unresolved. How many times did such mergers occur? Was the origin of mitochondria a single, rare event? Or did multiple attempts precede the successful lineage? Did chloroplasts arise once or through several independent captures across algae? The details blur in deep time, leaving only the certainty that symbiosis was essential and transformative. The vision is steady. In ancient waters, cells carry within them other cells, each performing a task the host alone could not. Energy is multiplied, sunlight is harvested, and complexity gains a new foundation. From quiet partnerships, the machinery of all later ecosystems is assembled. With mitochondria supplying steady energy and chloroplasts capturing sunlight in some lineages, cells begin to experiment with living together. At first, the unions are loose. Colonies of nearly identical cells clustering in chains or spheres, held by secreted gels or shared walls. But over time, cooperation deepens. Some cells begin to divide labor. One set specializes in movement, another in reproduction, another in feeding. The first stirrings of multicellularity arrive, not yet animals or plants, but something in between. The ironies are gentle. Multicellularity, which seems complex, begins with the simplest act of all, cells choosing not to separate after division. Another irony lies in scale. Organisms made of thousands of cells may be no larger than a grain of sand, still microscopic despite their unity. A third irony whispers across time. This profound step toward complexity occurs again and again, independently in algae, fungi, and animals, as though life finds the same answer from many different directions. Details remain in stone and molecule. Microfossils such as Grippania spiralis, coiled ribbons from over 1.5 billion years ago, may represent early multicellular algae. Filamentous fossils in Proterozoic shales hint at coordinated growth. Even today, living volvocene algae show transitional forms, single-celled Chlamydomonas, colonial gonium, spherical volvox with distinct reproductive and somatic cells. These living examples echo the ancient path, a continuum preserved in biology itself. Yet mysteries persist. Why did multicellularity arise when it did? Was it ecological pressure from predators, forcing prey to grow larger? Was it nutrient-rich? Oceans after glaciations that favored new forms of cooperation? Or was it simply chance, a possibility that succeeded and endured? The fossil record is sparse, leaving the earliest experiments only partly visible. Still, the vision is patient. In dim seas, tiny colonies drift, each a chorus of cells bound together. No drama, no sudden transformation, only a quiet persistence. Individuality yielding to collectivity, and the foundation of larger bodies slowly taking form. On the quiet, seafloors of the late Precambrian, new shapes appear. Soft-bodied organisms spread across shallow marine sands, leaving faint impressions that survive in stone. These are the Ediacaran biota, quilted discs, frond-like forms, branching patterns unlike anything familiar today. They are neither plants nor animals in the modern sense, but experiments in multicellular life, expanding into forms vast compared to microbial mats. The ironies are calm. The first large creatures leave almost no trace of bones or shells, only the delicate outlines of their bodies in silt. Another irony rests in diversity. Though their forms are strange and abundant for tens of millions of years, nearly all vanish without direct descendants. A third irony lingers in memory. They were once thought to be simple algae or inanimate structures, yet they represent the earliest attempt at ecosystems built from visible life. Details come from sites such as Mistaken Point in Newfoundland, Charnwood Forest in England, and the Flinders Ranges in Australia. There, bedding plains reveal entire communities frozen in place, fronds aligned with ancient currents, discs overlapping like imprints of coins, sprawling forms up to a meter long. Some resemble feathery leaves, some branching networks, some spirals or ovals pressed into fine-grained sediments. Their anatomy is still debated, but their presence is undeniable. Large, multicellular organisms living in coordinated assemblages. Mysteries remain deep. Were these creatures early animals, perhaps related to cnidarians? Were they giant protozoa, lichens of the sea, or a completely separate kingdom now extinct? How did they feed? By photosynthesis, osmosis, or filter feeding? The answers shift with each new fossil and model, never fully resolved. The vision endures. Across shallow shelves, soft gardens spread in silence, their outlines rippling with currents, their textures sinking slowly into sand. They are gone now, but for a moment in deep time, Earth holds a world of strange and gentle bodies, the first forests of the sea. In the next chapter of Oceans, complexity quickens. Around 541 million years ago, hard parts appear: shells, spines, teeth, and carapaces, giving structure to bodies and durability to the fossil record. This Cambrian diversification fills seas with forms that swim, crawl, and burrow, leaving traces not only of bodies but of behaviors. Trilobites scuttle across the seafloor, brachiopods anchor to sediment, early arthropods swim with segmented limbs, and the outlines of familiar body plans emerge in rapid succession. The ironies are quiet but sharp. Hard parts, which seem protective, also make organisms more visible to predators, fueling an arms race that accelerates diversity. Another irony lies in preservation. Creatures with shells are remembered in detail, while the soft-bodied majority remain hidden, though they may have been equally abundant. A third irony rests in time. What appears as a sudden explosion is in reality the product of slow buildup across millions of years, compressed in the rock record into a moment. Details sharpen the image. Sites like the Burgess Shale in Canada, Chengjiang in China, and Sirius Passet in Greenland preserve delicate fossils of soft tissues, gills, eyes, digestive tracts, alongside mineralized shells. Their diversity includes creatures with compound eyes, articulated limbs, and nervous systems complex enough to coordinate movement and sense. Trace fossils show deeper and more intricate burrows, evidence that animals not only lived at the surface but reshaped the sediment below. Mysteries remain. What triggered this diversification? Was it rising oxygen levels after Proterozoic glaciations, crossing a threshold that allowed larger and more active bodies? Was it ecological, the invention of predation creating new niches? Was it genetic, the expansion of developmental toolkits such as Hox genes? Each factor may have contributed, yet no single cause suffices. Still, the vision is steady. Oceans that once held only microbial mats and soft fronds now swarm with articulated forms. Light filters through shallow waters, glinting off shells and eyes. In the stillness of deep time, Earth holds a sea alive with motion, structure, and variety, the quiet beginning of animal life as we know it. While oceans fill with shells and limbs, the continents remain barren. On land, there are no forests, no grasses, no mosses even. Only rock, sand, and occasional microbial films darkening moist surfaces. Winds move freely across empty plains, carrying dust that settles into the seas. Rain falls on bare stone, leaching minerals and running in braided streams that shift channels with every storm. The silence of land is profound, a stillness broken only by erosion. The ironies are subdued. The continents, which one day will host vast forests and animals, of every scale, are at this time lifeless plateaus. Another irony is the contrast. Oceans teem with movement, yet only a few meters away the land lies motionless. A third irony lingers in process. It is the weathering of these sterile landscapes that sustains nutrients in the sea, feeding the diversity offshore. Details sharpen the picture. Ancient soils, called paleosols, preserve thin horizons of weathered minerals, often rich in iron but lacking any root structures. Cross-bedded sandstones show the work of winds unbroken by vegetation. Stromatolitic crusts coat the margins of rivers and tidal flats, low mats stabilizing sediment only in the wettest niches. Elsewhere, the surface is raw, exposed to ultraviolet light and unshaded heat. Mystery remains in timing. When did the first microbial mats extend beyond coasts into true terrestrial environments? Did small patches of green exist earlier than fossils reveal, perhaps in cryptic soils or shaded pools? The earliest steps onto land leave only fragmentary traces, and the true beginning of terrestrial ecosystems is difficult to pin precisely. Still, the vision holds. Continents lie silent under the sun, their surfaces rough with unbroken stone. All the richness of life remains confined to the sea, while the land waits in patient stillness for the slow encroachment of green. Along shallow coastlines where tides ripple over stone, layered structures rise from microbial work. These are stromatolites, built by mats of cyanobacteria and other microbes that trap and bind sediment, layer upon layer, until domes and columns grow upward. Some are only centimeters tall, others reach meters, a record of patient accretion through countless generations. In the Archean, they were abundant, scattered across tidal flats and lagoons, a visible signature of life long before. Animals stirred. The ironies are gentle. Structures so robust are made by organisms so fragile, filaments of cells no thicker than threads. Another irony lies in endurance. Stromatolites dominated for billions of years, yet today they survive only in a few protected niches. And a third irony is aesthetic. These layered rocks, once mistaken for lifeless mineral growths, are in fact monuments to some of the earliest ecosystems on Earth. Details remain sharp. Modern analogs exist in Shark Bay, Australia, and a handful of other sites, where microbial mats still build stromatolites under conditions too salty or harsh for grazing animals. The lamination reveals seasonal rhythms, light and dark bands, like tree rings, each marking cycles of growth and sediment capture. Ancient examples, preserved in rocks older than 3.4 billion years, carry the same forms: domed, conical, and branching, set in carbonates and sandstones now hard as stone. Mysteries linger. Did all stromatolite-like structures form biologically, or did some arise from purely chemical precipitation? How widespread were true biological mats, and how much of Earth's surface did they cover? And why, after thriving for so long, did they decline so sharply once animals began to graze? The answers remain partial, written in patterns of stone but blurred by deep time. Still, the vision is quiet. On tidal flats under a dim sun, low mounds rise as waves wash over them, their surfaces slimy with living films. With each tide, sediment settles, cells rebuild, and the forms grow higher. They are neither dramatic nor fast, but they are steady, and their presence endures in stone long after the mats themselves vanish. Beneath the oceans and across the continents, the surface of Earth is never still. Crust fractures, drifts, and collides, carrying volcanic arcs, microcontinents, and deep basins into constant rearrangement. Plate tectonics, though debated in its earliest timing, is by the Proterozoic and Phanerozoic unmistakably active. Subduction. Zones consume oceanic crust, rifts open new seaways, and mountain belts rise where plates converge. The face of the planet is drawn and redrawn with each cycle. The ironies are steady. Continents, which seem permanent and immovable, are in truth only temporary rafts, assembled and broken again. Another irony lies in mountains, symbols of stability and endurance, that are actually fleeting ridges, eroded as soon as they are lifted. And a third irony. The stability of climate, sustained by weathering and carbon cycling, depends on the very instability of tectonic motion. Details give the image depth. Volcanic arcs produce chains of islands, their slopes feeding ash and lava into the sea. Accretionary prisms, wedges of scraped sediment, pile along subduction margins. Rift valleys open with stepped faults, their centers filling with basalt flows and shallow seas. Shields preserve the cores of ancient continents, their roots keels of deep lithosphere that resist subduction. These features assemble slowly, yet over hundreds of millions of years they transform the map of the world beyond recognition. Mysteries remain. Did plate tectonics operate fully in the Archean, or did it emerge gradually from earlier styles of crustal recycling? Was the mantle hotter and convection faster, making plates smaller and more mobile than today? How continuous was the supercontinent cycle, and how much was shaped by chance rather than inevitability? The debate persists, etched into isotopes and metamorphic textures. The vision is calm. Continents drift in silence, their collisions forming mountains, their separations forming oceans. Nothing is fixed, yet the rhythm itself is enduring. A planet of shifting plates, balanced between motion and memory. Over spans of hundreds of millions of years, drifting plates gather into larger assemblies. Supercontinents form, hold together, and then fragment, only for the fragments to collide again. Columbia, Rodinia, Panotia, Gondwana. Each names a chapter in this long cycle of union and division. The planet's surface becomes a slow kaleidoscope, the continents meeting and parting in silence. The ironies settle gently. Continents appear singular and whole, yet they spend most of their existence as fragments. Another irony lies in their cycles. Mountains that seem eternal are ground down, while oceans, seemingly ephemeral, persist far longer than peaks. And a third irony is scale. Supercontinents dominate the map, but their outlines are reconstructed today only from scattered fragments and subtle magnetic signatures. Details anchor the vision. Columbia, perhaps the first great supercontinent, assembled about 1.8 billion years ago, sutured from cratons that now lie across multiple modern continents. Rodinia followed around 1.0 billion years ago, its breakup linked to rifting that opened. New oceans. Gondwana, forming in the late Precambrian, sprawled across the southern hemisphere, its margins hosting some of the earliest complex life. Each supercontinent left behind mountain belts, rift basins, and mineral deposits that mark its existence even after its shape is erased. Mysteries remain. How precisely did these continents fit together, and in what order did they break apart? Reconstructions rely on paleomagnetic data, matching directions of ancient magnetic fields frozen in rocks, but the record is incomplete and often altered. Did supercontinent cycles drive evolutionary bursts by reshaping climates and ocean circulation, or did life's timing only coincide with geology's rhythm? The connections are debated, the patterns clear, but the causes still obscured. The image is unhurried. Continents drift, converge, and scatter again, their movements too slow to witness, but inevitable across eons. The Earth writes and erases maps in stone, each line temporary, each cycle both ending and beginning anew. Beneath the restless surface, another clock keeps time. Radioactive isotopes, uranium, thorium, potassium, decay within minerals, releasing heat and transforming into daughter elements at steady rates. These clocks measure billions of years, turning crystals into record keepers. Zircons, with uranium atoms locked inside, tick through eons, their ratios of lead and uranium revealing ages beyond imagination. Other minerals, from micas to feldspars, preserve younger chapters, cooling histories written as atoms slip from lattice sites. The ironies are quiet. Mountains rise and vanish, oceans open and close, yet the passage of time is recorded most precisely in invisible atoms. Another irony rests in fragility. The same radioactive decay that can damage a crystal lattice also makes it the most reliable. Chronometer we have. And a third irony lies in perception. For humans, a lifetime is measured in decades. But for Earth, the true rulers of time are isotopes whose half-lives span billions of years. Details give substance. Uranium-238 decays to lead-206 with a half-life of 4.47 billion years, nearly the age of the planet itself. Potassium-40 transforms into argon-40, trapped in volcanic minerals as they cool, marking eruptions across deep time. Rubidium, strontium. Systems date ancient crust, samarium, neodymium tracks mantle differentiation, carbon-14, fleeting by comparison, records only the briefest, most recent past. Together, they form a suite of clocks, each suited to a different span, each measuring silence with precision. Mysteries remain. Did the earliest isotopic systems reset under the extreme heat of the Hadean, leaving gaps in the record? how accurate are reconstructions when later metamorphism disturbs the ratios? Can we ever fully recover events from Earth's first 500 million years, or is that chapter beyond the reach of isotopic memory? The answers are partial, glimpses through broken glass. Yet the vision persists. Tiny crystals hold within them the rhythm of radioactive decay, a pulse so slow it feels like stillness. With each half-life, Earth measures itself, keeping time. Not in days or years, but in the quiet transformations of atoms deep within stone. As supercontinents assemble and break apart, shallow seas repeatedly flood the low edges of land. Epicontinental seas spread across cratons, covering thousands of kilometers with warm, sunlit waters. These seas are rich with carbonate sediments, deposited by the quiet work of marine organisms and chemical precipitation. Their floors become broad platforms, hosting ecosystems that flourish in the shallows. The ironies are subtle. Continents that rise above the ocean are often drowned again, not by deep basins but by thin layers of sea. Another irony lies in preservation. The shallowest, most temporary seas often leave the most complete sedimentary records. And a third irony. Land itself seems permanent, yet through much of Earth's history, vast regions spend more time beneath water than above it. Details. Anchor the vision. Carbonate platforms grow from the accumulation of skeletal fragments, microbial mats, and lime mud. Stromatolites and thrombolites build mounded structures. Later, shelly fossils scatter across sea floors. Evaporate deposits mark places where shallow water dries, leaving salt and gypsum in rhythmic beds. The layering of these sediments creates sequences hundreds of meters thick, vast stone diaries of transgressions and regressions. Mysteries remain. How precisely did changes in sea level track tectonic movement, glacial cycles, or mantle dynamics? Did nutrient delivery from flooded continents fuel evolutionary bursts, or did shallow seas simply provide more space for life already present? Why do some intervals show extraordinary preservation of fossils, while others record little more than limestone and shale? These questions hover, answers partial and debated. The vision is steady. Imagine broad, warm seas spreading across low continents, sunlight filtering through clear waters, microbial mats carpeting the floor, and carbonate mud drifting down in endless quiet. For millions of years, the land that seems solid is instead sea, and stone records the memory long after waves withdraw. Within these shallow seas, a slow and steady process locks carbon into stone. Marine organisms, whether microbial mats, algae, or shelled creatures, build their structures from dissolved calcium and carbonate ions. When they die, fragments settle, forming lime muds that lithify into limestone. Over immense spans of time, entire mountain ranges will consist of this quiet accumulation, carbon drawn from the air and stored in rock. The ironies are layered. The most enduring record of life is not the bodies themselves, but the sediments built from their remains. Another irony lies in the chemistry. The gas that once kept Earth warm becomes entombed in stone, cooling the climate through burial. And a third irony whispers in scale. Each deposit begins as particles no thicker than dust, yet together they become cliffs and peaks that outlast oceans. Details bring the image into focus. Limestones preserve delicate laminations, ripple marks, and crossbedding from shallow waters. Fossil shells and microbial textures appear as ghostly outlines, sometimes replaced by sparry calcite, sometimes dissolved away, leaving molds in the rock. In some cases, entire reefs form from carbonate secretion, their frameworks later compacted into masses hundreds of meters thick. Dolomitization alters some deposits, magnesium replacing calcium, creating crystalline fabrics that shimmer in outcrop. Mysteries remain. Why do certain intervals in Earth's history favor massive carbonate deposition while others leave only thin records? How do shifts in ocean chemistry, magnesium to calcium ratios, alkalinity, or pH, influence which minerals precipitate? And what balance of biology and abiotic precipitation created the earliest carbonates before animals? Sculpted reefs. The answers vary with place and time, never fully resolved. The vision endures. Shallow seas, clear under a brightening sun, rain-lime mud upon their floors day after day. Microscopic fragments build quiet monuments, and in time, entire landscapes of stone will rise, carrying within them the memory of vanished waters and the carbon they once held. After the great oxygenation, the levels of oxygen in the atmosphere and oceans do not rise in a smooth ascent. Instead, they plateau, fluctuate, and drift across long spans of time. For hundreds of millions of years, oxygen remains below modern levels, enough to change surface chemistry, but not enough to fill the deep sea. The Earth enters what scientists call the boring billion. Though nothing about it is truly dull, the ironies are gentle. Oxygen, which seems bound for inevitability, lingers at middling levels for nearly a third of Earth's history. Another irony lies in life itself. Though oxygen could allow for greater complexity, most organisms remain small and simple, thriving in niches that need little of it. A third irony whispers in terminology. The so-called boring billion is a time of profound stability, yet without it, later revolutions might not have been possible. Details sharpen the vision. Geochemical proxies, chromium isotopes, molybdenum concentrations, sulfur ratios, reveal oceans stratified into layers, oxygenated near the surface, anoxic in the depths, and sulfidic in many midwaters. Black shales accumulate on seafloors, rich in organic carbon, while shallow shelves host microbial mats and early eukaryotes. The land remains bare rock for much of this span, though weathering continues to feed nutrients to the sea. Mysteries persist. Why did oxygen stall at intermediate levels for so long? Were biological feedbacks restraining its rise, with microbes consuming as much as cyanobacteria produced? Did limited nutrient availability cap photosynthesis? Or was tectonic recycling, burying organic carbon too slowly to tip the balance further? Each model carries some evidence, yet no full solution. The vision holds steady. For a billion years, the Earth breathes shallowly. Not the deep inhalations of later forests, not the suffocating silence of earlier ages, but a long, patient pause. Oxygen hovers at a plateau, neither vanishing nor overflowing, and the world waits in quiet balance. Deep within the planet, molten iron circulates in the outer core, generating a magnetic field that extends far into space. This geomagnetic shield deflects solar wind, a stream of charged particles from the sun that would otherwise strip the atmosphere molecule by molecule. Without it, Earth might have ended like Mars. Its air thinned, its water lost. Instead, the planet holds its cloak of gases protected by an invisible field. The ironies are soft but striking. The shield that sustains the fragile atmosphere is born from turbulence in the deepest part of Earth, a region never seen. Another irony lies in the strength of the field. Though imperceptible to daily life, it leaves clear imprints in stone, aligning minerals like compass needles that endure for billions of years. A third irony whispers in its reversals. The field flips polarity at irregular intervals, confusing compasses yet leaving no harm to life, a cosmic rhythm both chaotic and benign. Details endure in rock. As lava cools, magnetic minerals such as magnetite lock in the direction of Earth's field, recording ancient latitudes and polar wander. Stripes of alternating polarity on the seafloor, symmetric about mid-ocean ridges, provide direct evidence of spreading plates. Paleomagnetism becomes a diary of both field and crust, a record written quietly in mineral grains. Mysteries remain. How exactly did the dynamo begin? Did the inner core already exist in the Archean, or did it crystallize later, strengthening the field? What controls the timing of reversals, some lasting tens of thousands of years, others millions? And why? Do long intervals of stability, such as the Cretaceous superchron, punctuate otherwise restless flipping? The answers are partly known, partly hidden in fluid motions beyond observation. Still, the vision holds. Above the molten outer core, an invisible field arcs outward, bending the solar wind into spirals. Auroras flicker near the poles, lights, born of collisions in the high atmosphere. Beneath them, the air endures, the seas endure, all sheltered by a shield that never rests. The planet turns on its tilted axis, circling the sun with a rhythm that is steady, yet subtly changing. Seasons emerge from this tilt, shifting sunlight between hemispheres, driving cycles of warmth and cold, growth and retreat. Over longer timescales, orbital variations, eccentricity, obliquity, and precession imprint their own patterns, the Milankovitch cycles, which pace the advance and withdrawal of ice across continents. The ironies are gentle. The slight wobble of a planet determines the reach of glaciers and the rhythm of climate, while the immense forces of plate tectonics shape landscapes more quietly. Another irony lies in the scale. Orbital cycles measured in tens to hundreds of thousands of years leave clearer traces in sediments than events of shorter span. And a third irony: life itself evolves and adapts under conditions that appear constant, yet are endlessly modulated by celestial geometry. Details surface in stone. Rhythmic layering in limestones and shales records variations in sunlight and seasonality. Varves, thin annual layers in glacial lakes, capture not only years but subtle shifts in orbital pacing. In deep-sea sediments, oxygen isotope ratios from foraminiferal shells reveal repeated swings in ice volume and temperature, aligning with orbital cycles calculated far beyond human timescales. Mysteries endure. How long have these rhythms operated with stability? Were they as influential in the Proterozoic as in the more recent Pleistocene? Did glaciations of deep time respond directly to orbital forcing, or were they amplified and muted by tectonics, volcanism, and greenhouse gases? The interplay is complex, and the record, though patterned, is never simple. The vision is calm. A tilted planet spins beneath its star, its orbit shifting minutely but persistently. Sunlight waxes and wanes across latitudes, snowlines rise and fall, and sediment collects in quiet layers that mirror the dance of earth and sun. The seasons turn, and across deep time, their rhythm leaves stone as its only witness. On sea floors, of the Cambrian and beyond, new marks appear not as bodies but as movements. Burrows tunnel through sediment, trails meander across mud, and vertical shafts pierce downward where once only microbial mats lay flat. These trace fossils are the earliest clear evidence of animals actively reshaping their environment, stirring oxygen into mud, blending layers that had once been stable and laminated. The ironies are gentle. Behavior, more ephemeral than bodies, leaves marks that endure for hundreds of millions of years. Another irony lies in invisibility. The animals themselves are gone, but their absence reveals presence, a negative space more permanent than flesh. A third irony is ecological. Creatures small enough to vanish in an instant transform entire sea floors simply by moving through them. Details bring the image close. Simple horizontal burrows record grazing along microbial mats, their loops and spirals mapping foraging paths. U-shaped traces mark filter feeders that lived partly buried, water flowing through their tunnels. Vertical shafts show suspension feeders that pumped the overlying water. Bedding planes preserve resting marks, outlines of bodies pressed into soft sediment before rising again. These are not just fossils of form, but of activity, the stirring of life into stone. Mysteries persist. Which animals made these traces? Worm-like forms, early arthropods, or entirely extinct groups? How complex was their behavior? Instinctive meanderings or deliberate strategies? Did the Cambrian explosion of burrowing precede or follow the heaving rise in oxygen, and how much did each reinforce the other? The timing remains debated, evidence drawn from fragmentary horizons. Still, the vision is steady. Across shallow sea floors, animals leave paths in sand and mud, inscriptions of motion more enduring than the creatures themselves. Each groove and tunnel marks a quiet shift. The seafloor is no longer passive sediment, but a living fabric, continually rewritten by life. The silence of the continents begins to break. Along river margins and damp flats, the first green filaments creep from water to stone. These are early land plants, no taller than mosses, lacking roots, leaves, or flowers, yet they alter the landscape profoundly. By spreading across bare rock, they weather minerals more effectively, capturing carbon dioxide and binding soils. The first forests are only centimeters high, but their influence reaches into atmosphere and climate. The ironies unfold gently. Plants, fragile and small, transform continents more completely than glaciers or volcanoes. Another irony lies in scale. The earliest forests would hardly cast a shadow, yet their presence marks a turning point for the planet. And a third irony: while they draw down carbon and cool the air, their decay also enriches soils, preparing the ground for even larger plants to follow. Details linger in fossils. Spores with tough walls appear in Silurian rocks, resistant to decay, scattered like microscopic seeds across sediments. Cooksonia, among the first vascular plants, grows simple stems with sporangia at their tips, fossils no more than a few centimeters tall. Later, lycophytes and ferns rise taller, their vascular tissues carrying water and nutrients upward, allowing growth into forests. Roots spread into soils, fracturing rock and increasing weathering rates, linking land more deeply to cycles of carbon and climate. Mysteries remain. How gradual was the colonization of land? Did microbial mats and lichens precede true plants by millions of years, blurring the boundary? What role did symbiotic fungi, mycorrhizae, play in enabling plants to take hold on rock? Fossils give glimpses, but the earliest chapters are fragmentary, written in spores and impressions more than whole bodies. Still, the vision is quiet. Along stream banks and wet ground, small green shoots stand against stone, photosynthesizing in air. For the first time, their presence is modest, yet their consequence vast. The beginning of terrestrial ecosystems, the first hint of forests to come. Beneath continents that now hold the first patches of green, the mantle continues its restless work. Plumes of hot rock rise from deep within, melting the base of the lithosphere and feeding vast volcanic provinces. These mantle plumes leave fingerprints in the geological record: thick flood basalts, domed crust that uplifts and fractures, and mineral deposits formed by the circulation of heated fluids. The surface is shaped not only by drifting plates but by the slow fires that well upward from below. The ironies are subdued. The plumes that disrupt continents also help stabilize them, welding crust together with new intrusions. Another irony rests in their timing. The same eruptions that devastate ecosystems provide nutrients that fuel recovery. And a third irony: features so large that they span hundreds of kilometers arise from motions at the atomic scale, the slow rearrangement of minerals deep in the mantle. Details sharpen the picture. Large igneous provinces, such as the Deccan, traps, and the Siberian traps in later eras are products of plume-driven volcanism. In the Precambrian, similar but older events built basaltic plateaus and underplated continental crust. Kimberlite pipes carrying diamonds from deep sources are thought to mark ancient plume activity as well. The geochemical signatures, enriched isotopes of strontium, neodymium, and lead, trace their origins to mantle reservoirs long isolated from surface mixing. Mysteries remain. How stable are plumes over time? Do they root in the deep mantle or rise transiently from thermal instabilities? How many ancient plume events are hidden by erosion, their evidence erased except for subtle chemical clues? And how much did plume activity influence supercontinent cycles, triggering rifting and dispersal? These questions keep their answers muted, known only in fragments. The vision is steady. From the depths of the mantle, plumes rise like unseen flames, reshaping continents in silence. At the surface, basalt flows spread across land, thickening the crust. The slow breathing of the planet continues. Fire below and stone above, inseparable across time. Across the surface of cooling lavas and layered sediments, magnetic minerals align with Earth's field as they crystallize. For a time, they point north, but then, without warning, the polarity reverses. North becomes south, south becomes north, and minerals in new rocks record the change. These geomagnetic reversals occur irregularly, sometimes separated by hundreds of thousands of years, sometimes by millions. The crust becomes a striped archive, each band a record of polarity fixed in stone. The ironies are quiet. The compass, which seems steady and reliable, has flipped its direction countless times. Another irony lies in consequence. The field that reverses erratically still protects the planet continuously, never failing in its shield. And a third irony whispers in perception. What seems chaos to us leaves behind one of the clearest. Signals of order in the geological record, details sharpen in mid-ocean ridges. As basalt cools, magnetite crystals freeze with polarity aligned to the current field. Symmetric stripes of reversed and normal polarity on either side of ridges reveal the spreading of seafloor, proof of plate tectonics. On land, volcanic flows, stacked in sequence, capture successive flips, their ages dated by isotopes, building a timeline of reversal history. Paleomagnetism becomes both clock and compass, aligning ancient rocks with vanished poles. Mysteries remain. What causes the reversals? Are they triggered by instabilities in the fluid outer core, by changes at the boundary with the mantle, or by processes still unimagined? Why do some intervals, called supercrons, last tens of millions of years without reversal, while others flip rapidly? The dynamo remains hidden from direct observation, leaving models but no certainty. The vision is calm. A planet turns, its molten core flowing, its field reversing in rhythms beyond human scales. Rocks carry the memory faithfully, silent witnesses of a sky that shifted without sound. The field drifts, flips, and steadies, and through it all, the Earth remains protected. Within crystals and ice, tiny pockets of ancient air endure. In some minerals, gas bubbles are sealed during cooling, preserving the chemistry of vanished atmospheres. In polar ice sheets, each snowfall traps air that compresses into bubbles as it buries deeper, a record of climates stretching back hundreds of thousands of years. These inclusions are time capsules, silent witnesses of atmospheres, no longer present. The ironies are delicate. The vastness of Earth's skies is remembered most clearly in bubbles no larger than grains of sand. Another irony lies in fragility. Air that once filled an entire planet survives only where it is locked away. And a third irony, though invisible and weightless, atmosphere becomes heaviest when trapped in stone, enduring longer than the mountains above it. Details sharpen the vision. Gas inclusions in Archean quartz and barite suggest atmospheres richer in carbon dioxide and nitrogen, with almost no oxygen. In Proterozoic rocks, sulfur isotopes reveal photochemical reactions that occur only in an anoxic sky. In ice cores, layers record not only carbon dioxide and methane but volcanic eruptions, dust storms, and solar variability. Together they form a layered archive, connecting chemistry to climate across eons. Mysteries remain. How representative are these preserved samples? Do gas inclusions reflect local anomalies or the global atmosphere of their time? Can isotopic signals in ancient rocks be trusted after billions of years of metamorphism? Even in ice, bubbles slowly exchange gases with surrounding crystals, blurring the record at its edges. The atmosphere's memory is precise yet imperfect, enduring yet incomplete. The vision endures. Air once breathed by no creature or later by millions still lingers, in bubbles sealed away. Each tiny sphere is a page of history, a fragment of a vanished sky. In silence, the earth carries its own breath forward, hidden within stone and ice. Within the deep crust, crystals grow slowly, their edges adding atoms one by one as heat and pressure shift. These minerals often preserve internal zoning, rings, and bands that mark cycles of growth. Like tree rings, they record fluctuations in temperature, pressure, or chemistry, capturing rhythms of the Earth's interior. A single crystal can hold centuries, millennia, even millions of years of history in microscopic layers. The ironies are soft. Whole mountain belts may rise and erode away, yet their memory can persist in the concentric zones of a single mineral, grain. Another irony rests in scale. Processes vast enough to shift continents leave their imprint in spaces smaller than a hair's width. And a third irony. Crystals that seem uniform and unchanging to the eye reveal, under a microscope, a complex record of constant change. Details sharpen the picture. Zircons show cores of ancient age, surrounded by younger rims, each crystallization, event etched in uranium-lead ratios. Garnets grow zoned with manganese, iron, and calcium, recording the pressures and temperatures of metamorphism. Feldspars exsolve lamellae as they cool, thin streaks that testify to slow diffusion of ions, through a solid lattice. Each feature is a diary entry, silent but precise. Mysteries endure. How completely do these zones preserve their record? Do later heating events overwrite earlier layers, or do remnants remain even after metamorphism? How many cycles are missing? Because crystals dissolved and regrew, erasing earlier chapters? The answers vary with mineral and context, leaving every specimen partly clear, partly obscured. The vision is steady. In the stillness of rock, crystals accrete their rings in silence. Within them lies the cadence of deep time, pulses of heat, and pressure written not in words but in atoms. A hand lens reveals their sparkle, a microscope, their memory. The continents, once fragile rafts of lighter rock, begin to act as insulation for the planet itself. Their thick, buoyant roots extend deep into the mantle, slowing the loss of heat from below. Beneath oceans, thin. Basaltic crust allows easier cooling, but continental lithosphere, stable and rigid, acts like a blanket. This balance shapes mantle convection, directing plumes, altering circulation, and influencing the rhythm of tectonics. The ironies are gentle. The land that cools quickest at the surface also slows cooling most at depth. Another irony lies in contrast. Continents, which seem most exposed, are in truth the most shielded, protected by deep keels of lithosphere. And a third irony. The Very stability that preserves ancient crust arises from its inefficiency at releasing heat. Details sharpen in ancient shields. Cratons such as the Kapval in South Africa and the Pilbara in Australia preserve rocks more than 3 billion years old, their roots extending hundreds of kilometers downward. Seismic studies reveal these lithospheric keels as zones of unusual rigidity and low density, floating atop the convecting mantle. Their survival allows the accumulation of sediments, the recycling of nutrients, and the growth of stable platforms that persist through supercontinent cycles. Mysteries endure. How quickly did continents develop these thick roots? Were early cratons already underlain by keels, or did they thicken gradually through repeated underplating? How do these deep structures interact with plumes rising from below? Do they deflect them, channel them, or break them apart? Each question remains partly answered, glimpsed through seismic shadows rather than direct observation. The vision is steady. Continents rest high above the sea, yet their influence extends deep below. They hold not only soils and rivers but also hidden roots that shape the flow of Earth's interior. Silent and unmoving to the eye, they are the planet's great insulators, preserving both crust and memory across time. Through these long ages, geology and biology become inseparable. Rocks shape the chemistry of oceans, and life alters the chemistry of rocks. Microbes draw metals from solution, precipitating them into ores. Plants later weather stone more efficiently, then rain alone, releasing nutrients that cycle back into soils. The carbon silicate thermostat relies on both tectonics and living organisms, a feedback system where stone and cell share the same breath. The ironies are soft and patient. Life, which depends entirely on Earth's environment, in turn reshapes that environment more thoroughly than any physical process alone. Another irony lies in proportion. Microbes invisible to the eye drive chemical cycles larger than mountain ranges. A third irony. Geology, the study of what seems lifeless and inert, reveals itself as a record of life's constant interference. Details anchor the vision. Stromatolites bind sediments into domes of carbonate. Later, reef-building organisms create massive limestone platforms. Oxygen from cyanobacteria rusts iron into banded formations. Later, land plants accelerate silicate weathering, drawing down carbon dioxide and cooling climate. Black shales record organic carbon buried on sea floors, sequestering atmospheric gases in stone. The lithosphere becomes a canvas, biology its unceasing painter. Mysteries remain. How much of Earth's oxygen came from biological photosynthesis versus abiotic processes like photodissociation? To what extent did early microbial metabolisms shape sulfur and nitrogen cycles long before oxygen rose? How did life's influence compare with tectonic forcing and driving climate through time? Each feedback is partial, overlapping, and not fully resolved. Still, the image endures. A living planet breathes through stone and water. Cells alter oceans. Oceans alter crust. Crust alters mantle. Mantle returns gases to the sky. No clear boundary separates the geological from the biological. Earth itself becomes a system of feedbacks, a single, vast metabolism written across deep time. Across billions of years, patterns emerge in Earth's story. Cycles of oxygen, rhythms of continents, pulses of glaciation and warmth. To human eyes, these patterns resemble design, as though the planet followed a blueprint. Yet they are contingent, the outcome of chemistry, physics, and chance events repeated across eons. The world appears shaped for life, but its shaping comes from processes that have no foresight, only persistence. The ironies are quiet. Stability arises not from perfection, but from imbalance constantly corrected. Life thrives not because Earth was gentle, but because it was harsh, forcing adaptation at every turn. And another irony, the patterns that seem purposeful today were invisible in their own time, the outcome of countless accidents that only later align into coherence. Details remind us of contingency, the moon's stabilizing pull, born of a catastrophic impact, holds Earth's axial tilt steady. The carbon silicate cycle, blind and mechanical, keeps oceans liquid beneath a faint sun. Symbiosis between cells, improbable and singular, produces mitochondria and chloroplasts, the foundation of all complex life. Each turning point rests on events that might not have occurred, yet once they did, they shaped everything that followed. Mysteries remain, perhaps the deepest of all. Why did Earth alone among known planets hold liquid water for billions of years? Why did life arise here, and how early? How narrow was the window for oxygen to accumulate, for complexity to emerge? Are these inevitabilities written in planetary physics, or singular accidents that could as easily have failed? The answers remain beyond certainty, and perhaps always will. The vision is steady. Patterns stretch across deep time, appearing designed yet born from chance. The planet holds its history in stone, water, and air, a record not of purpose but of persistence. What seems intentional is simply the quiet unfolding of natural law, written in rhythms too vast for any witness. Across the span of Earth's past, ironies gather like quiet refrains. Catastrophes, which seem like endings, again and again become beginnings. The asteroid that ended one world of reptiles opened a world of mammals. The oxygen that poisoned ancient seas gave breath to later forests. The ice that locked the globe prepared the way for multicellular life to flourish once it melted. The first irony is scale. What feels sudden in geologic record may take millions of years to unfold, yet in hindsight it appears as a turning point. A second irony is permanence. Extinctions erase lineages forever, yet in the void left behind new forms arise that could never have existed otherwise. A third irony rests in perspective. To living beings, change is disruption. To the planet, it is continuity. Details remain written in stone. Boundary layers rich in iridium mark the end of the Cretaceous, fallout from a single impact that reshaped ecosystems. Glacial dropstones rest in ancient equatorial sediments, reminders that Earth once froze almost entirely. Red beds and banded iron formations preserve the slow oxidation of an entire world, transformations so vast they read like deliberate strokes. Yet each was simply the byproduct of process, amplified by time. Mysteries persist. How many times did life nearly vanish, teetering on the edge of extinction during glaciations, impacts, or anoxic oceans? Was survival always likely, or only a matter of improbable refuges? And how much of life's trajectory was shaped by random events rather than slow inevitabilities? These questions remain suspended, their answers partly hidden in lost intervals. Still, the vision is calm. Catastrophe and renewal are not opposites here, but partners. Each crisis leaves behind conditions for the next flourishing. In the stillness of deep time, irony is not sharp but soft. Endings dissolve into beginnings, and the planet carries on. Now the story rests in the present, though the present is only another moment in the long span of Earth's history. Continents hold their forests, seas teem with life, ice gathers and retreats at the poles. The atmosphere breathes with oxygen, clouds move in quiet cycles, and the magnetic field continues its invisible work. All the transformations of deep time converge here, not as conclusion but as pause. The ironies remain gentle. A planet that began in fire now appears calm beneath blue skies. Oceans, once green with iron, now hold coral reefs and whales. Continents that once drifted as scattered rafts carry cities and soils, and yet nothing has truly ended. Tectonics still shifts plates, the sun still brightens, cycles still unfold. The design that seems complete is only the latest arrangement of chance and change. Details remain in motion. Rivers carve valleys, glaciers grind stone, volcanoes spread ash, and sediments settle in layers that will one day become cliffs. Each process continues the same work that has always been done, only now witnessed. Every grain of sand carries the memory of mountains long gone. Every drop of water holds atoms cycled through oceans older than forests. The continuity is total, even when unseen. Mysteries endure. How long will Earth remain a living planet with oceans and air? How many more supercontinents will gather and scatter? Will oxygen one day wane as the balance shifts again? None of these answers are certain, and none need resolution for the vision to hold. The image is quiet. Earth rests for now, holding its history within stone, water, and sky. The deep time behind it is vast, the time ahead equally so. No design was required, yet the outcome appears shaped. In stillness, the planet carries its own memory, present in every fragment of rock and every breath of air. The story slows now, settling into stillness. Across billions of years, Earth has shifted from fire to water, from stone to air, from silence to life. Yet the planet rests as it always has, turning beneath its star, carrying the memory of everything it has endured. The rhythm quiets. Mountains rise and erode, oceans gather and retreat, but the pace is too slow to disturb the calm of this moment. Crystals still grow in the dark, ice still drifts at the poles, microbes still turn sunlight and minerals into energy. The processes that shaped continents and atmospheres continue, steady and indifferent, their motion hidden beneath the passing of days. There are no conclusions, only pauses. The Earth is not finished, nor beginning. It simply is, carrying its layered record in stone and water, the oxygen in the air, the salt in the seas, the iron in the crust. All are fragments of earlier worlds, recycled endlessly, never lost. To rest within this knowledge is to rest within time itself. The vision fades into quiet. Imagine the surface of the planet in darkness, clouds moving slowly above, waves touching coasts with measured patience. Beneath, rocks shift imperceptibly, as they always have. Above, the magnetic field bends starlight particles into faint auroras, shimmering at the edge of night. Everything is still in motion, and yet everything is at rest. There is nothing more to follow, no final word, only the soft rhythm of a planet turning, holding its own memory in silence. The end. Sleep well.